keeps on fast. Okay. Well, let's see what I have down here. Can you all hear me?
No.
The acoustics in this place are not all that good. So, yes. Here we go. Scientific research is based on the idea that everything that takes place is determined by laws of nature, and therefore this holds for the action of people. For this reason, the research scientists will hardly be inclined to believe that events could be influenced by prayer, that is, by a wish addressed to a supernatural being. This was Albert Einstein in 1936 responding to a child who wrote and asked if scientists pray. Okay. Well, now I wanted to go ahead and talk a little bit about the what happened this last year and other things, but getting on in years, it suddenly struck me I'd like to talk a little bit about what happened a long time ago. It was quite a while ago. Particularly, I was thinking about my boss in England, whose name was, what was his name? There again, you see, it's old age catching up with you. Well, Lisa Meitner was one of the two people involved, and also Schiff was the other. And what happened was, this time of year, they happened to be in Denmark, not in Denmark, in Sweden. And Lisa Meitner got a letter from her colleagues in Munich who had been working together, but she'd had to flee because of Hitler, and she was Jewish. And the letter said that they had this weird experiment where they'd put neutrons into uranium, and then they couldn't work out what was going on. Well, Otto and Lisa were finally got the idea that what happened was that the uranium split up, that the neutron went in, it upset the nucleus just enough that it split in two. Not only that, the question was, did it just split in two? But it didn't. It also produced one or two other neutrons. And so they wrote a letter to Nature about this, in which they said, this is what happens. He couldn't think what to do, and so they gave it a special name, and the name was fission. Before that, there'd been no word fission in the dictionary connected with physics at all. So we forget, you sort of think, well, fission, it's been there forever. That's not the case. That was the time they invented it. Okay. Well, oh yes. Before I really get started, I wanted to talk about the two books which are down here, which were published recently, and they were published by my son, who's sitting over there. Will you stand up? Then you'll know who it is. And there are two books there. They cost $10 a piece. You can put the $10 in the box. The money goes to the building fund. Now, what about this? This book is called God. That's a nice title for a book. And it arose because I used to go recruiting for graduate students with my friend Charlie Poole. Now, Poole was a devout Catholic, and I'm a Unitarian. But the thing was that Poole also suffered from this thing called narcolepsy, which means that you fall asleep suddenly and without warning. And he would drive, I would drive, and then we'd switch, and he would drive. And I was afraid that he would fall asleep while driving. Well, what do you do under these circumstances? I found the best plan was to get into a theological argument with him about the virgin birth, for example, or whatever. Well, this went on for quite a while, and finally we put these all together into a book, and Christopher here has published that, and that's down there, so you can have a look at it. And one of the good things, of course, Christopher is Catholic too, and one of the things that Unitarians are particularly agreeable to is that everybody should make up their own mind about religion. It doesn't matter what, but you make your own mind up. You don't merely take what is going. We've got on very well, pretty well together. He has what he likes, and I like, and that's a good thing, I think. Okay, well, the second book is called Tea at the Cavendish, and this has been somewhat why Tea at the Cavendish? You know, well, the Cavendish was the lab I was at, which was in Cambridge, and what had happened was that in 1900 or so, the professor J.J. Thomson, who discovered the electron, he gave a lot of money, in his will I think actually, to provide a cookie, or what we call a biscuit, for tea every day. So every graduate student got one of these biscuits and of course a cup of tea at 4 o'clock in the afternoon. So if you wanted to meet somebody, you always went up at tea time, because for sure you'd find them there. Who would refuse a free cookie? So that's why it's called Tea at the Cavendish. And of course this guy, Frisch, that I was talking about, he was our professor and he was there too. He brought his aunt, Lisa Meitner, who I was talking about, around to me and had me explain the work I was doing, which I did in English, and then he translated it into German. I was very surprised because I always thought Lisa Meitner had very good English. But anyway, I should say that Meitner is one of only two women that have elements named after them, like hydrogen and carbon and so on. These are the elements. But there's also one called Meinerium, which was named after her. So it's interesting, I think. Okay, yes. So, well, J.J. Thomson discovered the electron, Rutherford the nucleus, and Chadwick the neutron there, and I thought that was the end of it. That was when I went up there, but I was wrong. We all had little labs. On one side of me was a guy called what was his name then? Max Perutz. And he was working on hemoglobin. Nobody had disentangled just the molecular structure of hemoglobin, and he did. And long after I left, he got the Nobel Prize for that. On the other side of me, there was Watson and Crick, and I used to have tea with them. And they were working on this long chain molecule which had hundreds of radicals hanging off it. And they had no idea what the thing was at all. And don't forget, at that time, there was no clue as to how procreation of anything, of the human race, went on. Anyway, so they would use the techniques. It was terribly tedious work, one forgets that. They had to use what was called Fourier analysis, which was very tedious at that time, and also they found that other things connected with this analysis, what was called the phase problem. Actually, this guy Perutz, they with a lot of help worked this out. You could get
sort out the phase problem by putting a heavy element in this. But anyway, you're not interested in that, I'm sure. And that got rid of it. And of course, Watson Creek, well, they said, what did I think? And I said, well, I quit on this. You're never going to entangle this very complex molecule. Well, that, of course, was DNA. And they did disentangle it. And from being, at that time, there were perhaps a dozen people in England working on this kind of stuff. And now, of course, there are thousands and thousands of people working on molecular biology. So it just shows you can never tell. Okay, so that's tea at Cavendish. Yes. Well, of course, that wasn't the only thing going on. They were working on, for example, the radio astronomy, and in the fields around they put various radio telescopes, antennas of different kinds. So it was kind of interesting that things were not dead at Cambridge at that time. Well, what are your beliefs? Do you believe in a personal God? That's one whom you can pray to do something for you. God, I need $10,000. If you do, put up your hand. How many people believe in that? No? Okay. I'll read out the other things. How many people are atheists? No, one or two, quite a few, in fact. That's no God. How many are agnostics? They don't know. Oh, quite a lot. Okay. How many believe in a conventional religion? Christian, Muslim, Buddhist, etc. No, one or two. Yes. Okay. Trying to get these pages apart. Oh, here we go. Well, it's interesting to see. We have quite a lot of different beliefs here, and I think all of us, the thing about it is that all of us have generally thought about this and come to a conclusion one way or the other. Even if it's no conclusion, you come to that too. Okay. Well, the other thing, oh yes, I've got down here. We are still here, and the Earth will likely exist for the next 5 million years or so. But we won't. It'll be too hot. Because the Earth will, of course, get burned up as the Sun expands, and eventually the Sun will be big enough to... but, of course, this is the stuff that we're getting now, and this year, the particular interest has been... Well, one of them has been this... finding planets connected with stars nearby, and they found hundreds and hundreds of planets now. We used to have a guy who came around, he was Dutch, and the Dutch are very keen on astronomy, and every year he'd come up with how he had found this new star, this new planet. Well, it turned out it was his equipment that was bad, so he hadn't really found the planet, but now they have. And the system for finding planets is very specific. Basically, there are two things that tell you whether you have a planet. One is that the planet, as it goes in front of the star, casts a shadow. So as you're looking at the star, even though you cannot see the planet, you see that the light from the star goes down. And when the planet moves out of the, so it's no longer casting a shadow on the star, then it goes back up again. So you can time this and so on. So you know the period of the planet, how long it takes to make one revolution around the star, and to some extent, because of the timing, you can tell how far off it is and this kind of stuff. So that's one way of doing it. The other way is you look at the star and see it wobble. So if it wobbles, what is happening is the planet is attracting the star, and the two of them are actually going around one another. so that the star itself will wobble to and fro, and we can time that and measure it and so on. But those things don't tell you anything about what's on the planet. You know, what would it be possible to have life or not? And it's as time goes on, I'm quite sure that you'll be getting more and more information because they have techniques, what with the satellites and so on, of looking at stars more delicately. So that's for the future. Okay. Oh yes, and the other thing that's interesting is LIGO. We knew that there are 4 forces in the universe, and only 4. There's the electromagnetic force, there is the strong nuclear and the weak nuclear, and then there's gravity. Well now, these other things, electromagnetic, strong nuclear, weak nuclear, have particles associated with them, but gravity never has. And this has been a worry ever since Einstein, because of course he predicted that would happen, that you would have a particle associated with it, called a graviton. And now we've found it. This is the thing, you probably read about it, that there is a detector, one in Louisiana and the other one on the west coast. And they saw a sharp spike in the reception. It's a very complicated and expensive device. There is an evacuated tube miles long containing a thing called a Michelson interferometer. And you look at this, and if you're lucky, you see this change. What is surprising is that they saw one, the very first one last year, but made a fuss about that. But they've seen another one. Well, they thought they'd have one every 100 years or something. And to have 2 so close together is really very surprising. So, of course, now everybody in his uncle is building another of these detectors, like in Germany and so on and so on. So I'm sure we shall hear some more about that. Oh yes, and the Nobel Prize is here. Michael Koslitz, David Fowlis, the third one is, and they discovered that the change in phase of things like from water to ice and so on, it's a sudden change. That is to say, you can't have it half ice and half water, a substance like that. It's either water or it's ice. And this is really interesting. And they found that this was due to a mathematical thing called topology. So we now know of many topological phases, not only thin layers, because they worked on very thin layers on different materials, but also in ordinary 3-dimensional materials. Well, what is topology? It's a mathematical concept that accounts for how certain physical properties are related by smooth deformations. A football can be smoothly deformed into a rugby ball. You know, one is long, that is, they have the same topology. But neither of these can be smoothly deformed into a bicycle tube, because it has a hole in the middle and so on, which therefore has a different topology. The laureates recognized how novel states of matter could arise due to the differing topologies and how the underlying particles arrange themselves at the microscopic level. As an example, how do you capture lions using topology? This used to be a joke, that kind of thing. Well, you build an enclosure so that you are inside the enclosure and the lions are outside the enclosure. And then you perform a topological transformation. That's a mathematical thing. And if you perform that topological transformation, the lions go inside the enclosure and you go outside. Now, I'm quite sure you don't understand that. But if you look into on the web, you'll discover a lot about topology as a mathematics. For example, also quantum mechanics depended a lot on another type of mathematics that they called group theory, which they didn't think would
ever be interesting. I mean, now, it's, of course, it's very fantastic. Okay. Well, yes, Congress last week gave funding for various things. The BRAIN initiative, so just as they had funded space research going to the moon, that was a long time ago. Now they are going to give a lot of money to BRAIN research. It's called BRAIN, B-R-A-I-N, in the initials. Anyway, that's $1.5 billion for that. Cancer, the cancer moonshot, that's the other thing they're giving a lot of money to, 1.8 billion. And the precision medicine initiative, I'm not quite sure what that is, but all of those you're going to hear a lot about in the next 10 years, because they're going to get funded, and we shall find out how the brain works, which we still don't know. Of course, with some of those it doesn't matter, but still. Okay, well, I've mentioned this planet, Proxima B, Proxima Centauri, and the Proxima B, and I think this is, well, I had mentioned that, I forget what I talked about, about going back to history, about Bohr and a guy called Wheeler, who gave the first paper on the liquid drop model of the nucleus as to how it split up in fission. Well, Wheeler also did the black holes and the wormholes, but he's a southerner, so he's been here once or twice, and in fact, I chatted with him one time. He was talking about these three particles that make up a certain portion of matter. He says, just like gasoline, it comes in 3 times, you know, whatever they may be. But anyway, the other thing that interested me in how all these things tie together is you had a sermon 2 weeks ago by Gloria Telko. What is it, Telko? Yeah. And what's interesting about that was she was Wheeler's secretary. Wheeler was at Princeton, but also at Texas, and she was his secretary there. So the guy who actually started the atom bomb thingy was this guy Wheeler, and she worked for him. So, well, I think probably my 20 minutes is up, is it? If not, I could mention that Wheeler came up with these concepts which now are partly into a part of cosmology. But you have to be careful. You should never believe a cosmologist, because they come up with these wild theories, and sometimes these things work out and sometimes they don't. In Wheeler's case, he was very perceptive. He actually wrote a book on gravity, and it's an enormous book like that, and he said, you know, if you're writing about gravity, you have to put a lot into it, and it weighs a lot more. Anyway, he was here a few times, and it's the idea of the black hole, of course, is that you have a star so dense that anything that falls into it can't get out. It just goes in, and there's a horizon. And it was thought for a long time that you couldn't get, this was it. You'd never learn anything about the inside of this thing, because anything that went in couldn't come out. Well, there was this English physicist, what's his name now? Hawking? The one, Stephen Hawking. Yeah, Stephen Hawking, that's right. Stephen Hawking, who showed that in fact you can get radiation, if it's hot enough, coming out of this black hole. So this has altered our view of the universe, strangely enough. It doesn't sound like much, but it turns out to be a lot more than we originally thought. And then there is entanglement. Now, if you want to really upset a physicist, just mention entanglement, and you'll see his eyes light up.
because what that boils down to is that you thought that you couldn't have anything travelling faster than the speed of light. Okay, that was what Einstein said. But it turns out that you can, but it's rather weird. And so you have the original. When I first came here with my colleagues, Ernst Breitenberger and Ed Lerner, we got working on this. The EPR paradox is called Einstein, Paninsky and Rosen. And it's still a paradox because what happens is if you split a particular object, a particle apart, and it goes to opposite ends of the universe, and you make a measurement on this one, it affects the one at the other end. But it's, again, that's something which I'm quite sure you don't understand, but then neither do I, neither does anybody else. But the question is does it actually happen? And this is called Bell's theorem, and it actually does happen. So now, of course, there's a lot of people working on why this is and so forth and so on. But it's one of those things. So that's that end of things. These cosmological problems are likely to beset us for the next several years. It's like the other thing is that 85% of the universe is dark matter. And you might think, well, if 85% of the universe is dark matter, we should know what that is. But we don't. We don't know what this dark matter is at all. They've been making measurements. There are various, what they call WIMPs, weakly interacting massive particles that they think it might be. But all the experiments to find this stuff have failed. So then again, you can really get people worked up about that. But maybe we continue to look for it, but of course we haven't found it, and it's likely that maybe there's something else there that we don't know about. There's always that possibility. Okay, time's up.
Now it's time for sharing our abundance.